guys, and welcome to another video in my series of videos on electromagnetism. This is going to be probably the final video covering some of the preliminary maths that you'd need for electromagnetism. This is probably going to be like the hardest set of maths that you'll need, so this is stuff that will only come up in quite specific cases, and you won't need to know the full details of it. I'm just going to go through just for a bit more background, just so that you guys can understand what these concepts are about, and a little bit more about how they're derived. But you probably won't need to know anything about the derivation in probably either your maths course or your EMAG course that you're doing. So don't worry too much about the derivation, but I will be going through it just so that you guys can understand. So the first thing I'm going to go over is something called the Dirac delta function. Now, what the heck is this, you may be wondering? Well, the Dirac delta function is kind of a little bit of a cheat for physicists. It's kind of a physicist cheat. It's quite an important concept, and basically the idea behind it is that nature isn't smooth, and you need some kind of way of describing something that is what's called infinitely localized. So say you have, you have this sort of blank region of space right here, and you have nothing throughout the entire region of space apart from this one tiny little dot right there. That's the only thing. So how are you going to kind of represent that in a mathematical way? Well, typically if you were to maybe like draw a graph of something, so let's say this is kind of some kind of density graph. Whoops. Then you're going to have nothing for most of it, but then you're going to have this kind of infinite like spike at this one position right there. So it's going to be this infinitely thin but infinitely tall spike, and this is exactly what a delta function is. We normally represent it as delta of x, and it's that right here. It's basically an infinitely thin and infinitely tall spike at one particular location. So there are several different functions which are kind of similar. I will just go over two. You can have what's called a top hat function. And the reason it's called a top hat function is because it resembles a top hat, and it's kind of like a finite width about this kind of one point right here. And this is similar to a delta function, except it's actually got a finite amount of width associated with it. Whereas obviously a delta function, it's infinitely thin and infinitely tall. So basically we can say that in the limit, this top hat function becomes a delta function. And likewise, you can describe it with something called the sinc function. The sinc function is a function you'll probably come across many times. It's the function that describes diffraction. It's actually defined as sine x over x. I've actually drawn it with a little bit of a shift right here. If it was strictly sine x over x, it would be centered about the x equals 0 point, but I've actually drawn it with a little bit of a shift. So basically, if this kind of peak, this kind of spike right here, was infinitely thin and infinitely tall, then it would be a Dirac delta function. But the way in which it's actually defined is not as this kind of infinite spike at this one point. The way in which it's defined is that the area underneath a delta function, so this area right here, is always 1. And so say this position right here, this is the x-axis, which I'm going to represent with lowercase x. This position here is capital X. This is just some arbitrary value of x. Then the way in which we define the delta function is that the integral, and this integral is across all space, and so of course the domain of all space of x is between minus infinity and plus infinity, so that's why we write that. The integral of a delta function, which the way in which we write that it's localized around this point x, is by saying of x minus x. If it was just Dirac of x, that would just mean it's localized around 0, basically. But this basically means that it's a Dirac function that's localized around this coordinate x right here. So that's just what that means. If we integrate that all across x throughout the entire region of between minus infinity and plus infinity, we'll get 1. So that is actually how a Dirac delta function is more properly defined, is that the area underneath the delta function is always 1 right here. So that's an important property. And the dimensions of a Dirac delta function in this kind of representation, this Dirac function has units of meters to the minus 1. Obviously, if you multiply this by this, you're going to get something dimensionless. Obviously, 1 is dimensionless as well. So that implies what the units of a delta function are. But one of the most important properties of delta functions is what's called the sifting property of a delta function. And say we have a function. The best way to represent this is kind of graphically. Say we have a function, I don't know, it's going to be some random function, maybe looks a bit like that, kind of like an x squared type function. And this is f of x right here. And this is, of course, x. Now, what we can use is we can use the delta function as kind of like a kernel. And what this delta function will do, it will pull out the value of x at which the delta function diverges to infinity. And so what I mean by that is that if we pass this function through a delta function of x minus x, and we integrate this throughout all the space, so we multiply the function by the Dirac delta function, and we do this for every single point across space, then, well, since this delta function is infinitely localized as a point, then there's only going to be one particular point at which you're actually going to get anything, and that's going to be the value of f at this one localized point x. Because everything else is just going to be 0, isn't it? So, because the Dirac delta function is 0 at every other point apart from this one point right here. So, say you've got this point here. Well, f of x may well be something finite, but at this point here, the Dirac function is just 0. So, obviously, if you multiply anything by 0, you're just going to get 0. So the only point that you're going to get something that's not 0 is this point right here. So what it's doing is it's pulling out the value of x in which it is not 0, which is this capital X right here. So if you look at it, there's no integration to be done. Like, you wouldn't integrate it normally, which is kind of cool. It's kind of very, very neat, really. So say if you had something like the integral between minus infinity and infinity, say you had some, I don't know, quite complicated looking polynomial function, x to the 4 plus x squared plus 1 or something, I don't know. And say you pass this through this Dirac kernel that is x minus 3. Well, what's the value in which it's going to blow up? What's this kind of infinite spike value? What's this x value? There's going to be a value in which it blows up. What is that value? Well, of course, it's 3 right here. As you can see, Dirac of x being 3 minus 3 is when it will be 0, and that would be when it blows up to infinity. And so you simply can just chug in 3 into this equation here, and you're going to get 3 to the 4 plus 3 squared plus 1, which is 91. So it literally just pulls out the value at which it diverges to infinity, and that's an important property of the Dirac delta function. And just as a kind of a quick kind of side note, you can generalize this pretty easily to 3 dimensions, and the way in which you do that is you say you're in 3D space right here, and say instead of some infinite spike, you've got this kind of point thing that I mentioned earlier. So say it's, I don't know, it could be an electron or something, located throughout this region throughout space. Say it's got coordinates x, y, z. Now, the way in which you could represent the electron density as like a mathematical function is that you can do that very easily with this Dirac delta function. So rho is the mass density, which is a function of position, and it's basically going to be the mass of the electron, but it's going to be multiplied by this Dirac function, which is going to be of units meters to the -3, and it's going to be localized at this point right here. So in 3 dimensions, this is going to be the 3D position vector r minus this 3D position r. So this is the vector position corresponding to this point right here, and so that's what it is in kind of 3-dimensional notation. You can also simply write it as a product of 1-dimensional Dirac functions. So x minus big X, y minus big Y, and z minus big Z. So that's how you can represent the density. And to get the total mass of everything throughout all space, what are you going to do? Well, you're going to integrate the density over the volume, over the entire volume. And this volume is going to be throughout all space. So it's going to be between -infinity to infinity, but it's going to be in all 3 dimensions. So you're going to have 3 integrals right here. So you're going to have an integral all between -infinity to infinity throughout the 3 different position coordinates. So you're going to have a Dirac function of x minus x. You're going to have a Dirac function of y minus y, all multiplied by Dirac function of z minus z. And this is going to be integrated throughout dx, dy, dz, because of course we're in a Cartesian representation, and so the volume integral is simply just the product of the 3 1-dimensional elements. So that's what it's going to be. Also, there's going to be the actual mass of the electron right there. And I hope you guys can see that this is just going to simplify to 1, because we know that the area underneath this, like any delta function, or any 1-dimensional delta function, is simply 1. And so you're just going to get me times 1 3 times, 1 times 1 times 1, which is still 1. So you're just going to get the mass of the electron. And that should be pretty obvious if you work out the mass of the entire thing, and throughout the entire thing all there is an electron, then it's pretty obvious that the total mass is just going to be that of the electron. So we've kind of done a pretty obvious thing, but we've done it in a way in which proves how delta functions work, which is cool. So yeah, that is the Dirac delta function. So next we're going to come on to something which is called the Divergence Theorem. Now this kind of goes back to calculus a little bit more. This is going back to the vector calculus that I taught in the first video. Now if you're unsure of what divergence is, then you're going to want to look away now and go and watch that video, because this is going to rely on the divergence property of vectors. So what we're going to consider is we're going to consider some kind of volume of space, and to do that I'm going to draw it in blue. There's going to be some kind of volume of space right here. So this is a volume of space. This isn't a surface, this is a volume, and it's going to have some charge in right here. So all throughout this space right here there's going to be some charge, and it's going to have a charge density, not mass density, a charge density of rho, and so rho I'm defining to be the charge per unit volume, so Q over V if you like, or dQ by dV, and it's going to have units of coulombs per cubic meter. Now, the flow of charge density is called the current density. And the current density is actually a vector quantity. We give it the symbol J, and it's a vector quantity. And what it actually is the current divided by the area, or as a differential, di by ds, right there. So that is the current density. So what is the relationship between charge and current? You guys probably do know this. Well, the current is simply the rate of change of charge, right here, dq by dt. So how can we represent that? Instead of representing it in terms of I and q, which you guys are more used to, we're going to represent that in terms of rho and j. And it's going to be a little bit more complicated because, of course, now we're dealing with densities rather than sort of things which are kind of more visible. So how are we going to do that? Well, if we remember what the divergence is, the divergence of a vector quantity gives how much it either increases or decreases, right? So there were two cases, remember, or three cases. If the divergence is greater than 0, then that means at that point it's increasing, or there is a net increase. There's more flux going out than there is coming in, so it's acting like a source. So if the divergence of J is greater than 0, then that means that there is, in this volume right here, then there is a net decrease of charge per unit volume. There is a net decrease. Now, why do I say there's a net decrease? Well, if current's flowing out through here, then that means that where's this current coming from? It's going to be coming from this charge right here. If there's charge inside and we find that there's more current going out than there is going in, then that must mean that charge is leaving the volume right here. So that must mean charge is leaving. So this is the first case. So what's the other case? Well, the other case is that the divergence of J is less than 0. And that means that there's more J going in than is going out. So in this case, the arrows will be kind of reversed. And so you're going to have more current flowing in than current flowing outwards right here. And what's going to happen? Well, if you've got more current flowing in, then that must mean that the charge in this region is increasing right here, because, you know, this charge has got to go somewhere, right? If there's charge coming in, then that means the charge inside this volume is going to increase with respect to what it already was. So this is quite an important thing. You're going to probably come across it quite a lot in physics, and it's called the continuity equation. So what can we say about the divergence of J? Well, we can say that the rate of change of charge is equal to the divergence of J, and that is minus d rho by dt. So that means that if, it's probably easier if I put the minus sign on this side. So charge is going to increase over time if the divergence of J is negative. So that's basically this case right here, in which more charge is entering this volume than is leaving. Alternatively, if more charge is leaving than is entering, then that must mean that this quantity is going to be negative. And so since this quantity without the minus sign is positive, and this negative sign will make it negative, so that kind of works, that kind of balances out. And this is called the continuity equation. Very important. And it's not just the case for charge, it's going to be the case, you're going to see this for other quantities such as mass and heat flux, and also diffusion if you do biophysics. So it's going to come up a lot, and this is called the continuity equation. So you guys can see why it's called the continuity equation. It's basically saying that if throughout this surface there is a current, it's going to have an impact on what's inside this surface right here. It's going to have a direct impact. So if there's more current that's going in, that's seeing like a current density going in this way rather than current density that's going out that way. If there's more going in, then that must mean that the total amount of charge inside this volume, which is bound by this surface, is increasing. And that's what the continuity equation is telling you. Now, when I was talking about divergence, I mentioned this quantity called flux. And flux, I said, was the total amount of sort of field that is kind of exiting a certain area. So how do we write this mathematically? Well, flux, which I gave the symbol phi, the kind of a simplistic representation is the flux density of a vector field, which I'm going to call A. I'm going to just call this vector field A. So this is kind of like our arrows right here. These are what these are what A is. It's the flux density dotted with ds right here. Obviously, it's going to matter what angle the flux is entering from. Obviously, you're going to get much more flux if the flux density is heading straight through this area right here than if you have something like, you know, this. You know, obviously you're not going to get quite as much flux, but that's taken into account by this dot product right here. So in fact, that should be an infinitesimally small amount of increase of flux. So how do we get the total flux? Well, we have to do it over the entire surface. So the total flux phi is going to be the surface integral of the flux density A integrated throughout this entire surface. Now, we actually write a little ring around these two integrals, and this shows that it is a closed surface. This surface has to be closed. It cannot be an open surface. It must be a closed surface. And the total flux that is going through a closed surface is given by this right here. And the reason why it must be closed is because if we think about a volume, if we think about our little volume of space, then the only surface that can fully enclose this volume, so if we imagine it's kind of, you know, getting like a suit of armor on or something, then, you know, the only surface must be closed. You know, it mustn't have any holes in at all. Otherwise, this won't work. Otherwise, we're going to miss out on valuable flux if there's no, if there's some holes and stuff in. So it must be a closed surface, and that's what this little ring right there is telling you. But remember that the divergence of a vector field is the net flux per unit volume out of an infinitesimally small volume. That was kind of what we said before. We said that if it's producing stuff, then there is a positive divergence. If it's acting as like a sink, then there's going to be a negative divergence. And so how do we write this in terms of this? Well, we write this as the limit in which the volume tends to zero. So we have to imagine some infinitely small limit of the flux per unit volume. And the flux, of course, we said was this right here. So this big integral right here, it's the integral of A all throughout the entire surface, integrated across the entire surface, divided by the volume, which is dV, and that's an infinitely small volume. So as dV tends towards zero, then the divergence of A it's the net flux that is either entering or leaving the surface. So that's kind of a mathematical way of expressing, you know, whether it's acting as a source or whether it's acting like a sink right there. So I'll put a little box around that, but this is not the divergence theorem. We're nearly at the divergence theorem. So what I'm going to do is I'm going to move this dV up onto this side right here. So the divergence of A all multiplied by dV is equal to the integral, this surface integral right here of the flux divided all dot producted with the surface, so the flux density rather, dot producted with the surface right here of this vector field A. So to deal with a finite volume, the question is, can we sum over these? And so let's go ahead and sum. So let's imagine our volume right here. Let's draw it in blue again, since that's the color we've been using. Let's kind of, imagine that this volume is made up of loads and loads of infinitely small volume packages right there. So these are all really, really, really small volume elements. I'm drawing them in Cartesian as cubes just to make things easy. So let's add them all together. So what we're going to do is we're going to sum over every single infinitesimal volume. And so what are we going to have on the right hand side if we do that? Then, well, we're just going to add together all of these as well. We're going to add together all of the various net fluxes in and out of each of the infinitesimal volumes. So we're going to have the sum of an integral right here. I know it's looking a little bit ugly, but bear with me just a second, because if we take the infinitesimal limit, then we find that this sum right here is an integral. It's actually a volume integral, and I hope you guys have done volume integrals. I know I didn't cover them in this basic mathematical thing, but this is just kind of like a sort of a very kind of quick overview. So in the infinitesimal limit, then this is going to be a volume integral, which is of course 3 integrals of the divergence of A over dv. Now, since A flows out of one element into the next, so if we imagine our vector field right here, it's going out of one little element, but it's going into the next, then all of the surfaces, if we think about it, all of the surfaces on the right hand side are all going to cancel, and so basically the right hand side is just going to become an integral over the whole surface, this kind of surface that's binding this volume right here, over that, and because all of the ones that are kind of facing each other inside the surface are all going to cancel each other out, because of course the flux exiting here is just going to be exactly the same as the flux entering here, bar the minus sign. Obviously the minus sign means it's going to cancel, which means that the only contribution to the flux is going to be on the ones at the border, the ones at the boundary. And so on the right hand side, we can simply replace this with the total integrated net flux of the surface right here. And this is the surface that's binding this volume right here. So this is a volume integral. This is a 3-dimensional integral throughout this entire volume right here. And this is the surface integral, which is across this surface right here that's binding this volume right there. And that, you'll be pleased to know, is the Divergence Theorem. And it's basically saying that the net flux of a vector field coming through a surface A is directly related to the divergence of that flux, all integrated across the entire volume that's bound by the surface. And the key thing is that this volume right here is what's called enclosed by the surface right here. So this outer surface, this outer shell, this outer kind of piece of armor, if you like, is binding the volume right here. So that is the divergence theorem, and it's very useful, particularly in Gauss's law, which we're going to come on to, and it's very useful for converting between Maxwell's equations. Actually, you can actually convert from the differential equations to the integral equations by using this right here, the divergence theorem. Of course, I'm going to show you how that works in practice. So yeah, that's the divergence theorem. So lastly, we're going to talk about Stokes' theorem. And so what is Stokes' theorem? Well, I'm going to sort of semi-derive what it is. I'm kind of more going to motivate it rather than like derive properly what it is. But it's all about the, similar to how the divergence theorem was all about the divergence, Stokes' theorem is actually all about the curl of a vector field. So So what I'm going to do is I'm just going to draw out what a typical vector field which has curl will look like. So it will typically look a little bit like this. So as you can see, you know, it's kind of like the arrows are not parallel. The arrows are all, you know, all kind of orbiting, if you like, a certain point right here. So this is what a vector field with a non-zero curl will look like. And so say it's some kind of, you know, maybe not an electric field, but say it's some kind of field that we're doing work against. So what we're doing is we're moving this particle, we're moving it through this vector field back to its original point. The point about this is that this integral, unlike what I was saying in the last video about about the work done by conservative force being independent of path, generally this is not the case. And basically the way in which you tell whether it is the case or not is whether this integral is closed. And the way in which we mathematically represent this integral is of a dot dl. So we're moving some sort of particle through this vector field A, and we're doing it for an infinitesimal length dl, and we're integrating that throughout the entire loop right there. Now this actually has a very close resemblance to curl, and I'm going to basically show how the two are similar. So what I'm going to do is I'm going to consider a rectangular loop right here. So this is a rectangular loop, and this loop kind of represents like a path kind of thing. So what I'm going to do is I'm actually going to divide this path up into 4 different segments. So here are the 4 different segments. I don't know why I wrote 4 then. 1, 2, 3, and 4. And we're going to go around this loop in the kind of anti-clockwise direction, if you like. So we're going to go around it in this way. So how can we break apart this closed loop integral? Well, in this particular geometry, this rectangular geometry, it's simply going to be the sum of 4 straight line integrals, as you can see right here. So there's going to be one integral which corresponds to this part of the path, another one which corresponds to this part of the path, one for this one, and one for this one. So you can break it down into 4 different straight line integrals. And of course, straight line integrals are pretty easy to evaluate. But before I do that, I'm just going to give these some coordinates. So we're going to call this point right here x0 and y0. And these sort of parts of the path are very, very small. We can consider them to be infinitesimally small. And so this point right here is going to be x0 plus a small, infinitesimally small change in x. So that's going to be x0 plus dx. But of course y hasn't changed, still the same y position right here. Remember our axes are x is going to be along this way and y is going to be along this way. Now for this point right here, x is going to be exactly the same, so it's still going to be x0, but y is going to have an infinitesimally small increase in y right here. And for this part of the path, both of which are going to have the small increase. This is going to be x0 plus dx, and this is going to be y0 plus dy. So those are our 4 positions which are being joined together by these 4 parts of the loop right there. So basically what I'm saying is that this closed loop integral in this particular case is going to be the sum of these 4 different integrals right there. So it's going to be number 1 plus number 2 plus number 3 plus number 4. And what we're going to do is we're only going to consider the parts in which x is changing. So to begin with, we're going to just think about this part of the loop right here, part number 1, and part number 3. So we're going to go back to the whole thing before, but we're just going to have a look at parts 1 and 3 to begin with. And as we'll find, parts 2 and 4 pretty much do exactly the same as what parts 1 and 3 will do. So yeah. So along path number 1, let's just think about what's going to be happening, what the integral is going to be along path number 1. So the integral of a dot dl across this path is simply going to be the x component of a, because remember a is a vector and we're only interested in the x component because of course this is only along x, and this is going to be evaluated at x naught, y naught, so whatever value a is at this particular coordinate, multiplied by dx, because of course that's how far along we've come. We've gone from x naught to x naught plus dx, so we've come a distance dx right there. So, and there's also going to be some higher order terms that we're not going to bother about. Now, what about along path number 3? What's the integral going to be for path number 3? So we're going to have a dot dl for this part of the path. Well, we're going to have a minus this time, because of course we're going in the other direction. Ax is still going to be the x component, but this time it's going to be evaluated at a slightly different position. It's going to be evaluated at x naught, but instead of y naught, it's going to be at the slightly higher y position, because of course part 3 of the loop is at a different y position than part 1 of the loop right there. And again, this is going to be multiplied by dx, and there's again going to be some higher order terms. I'm not going to bother writing that in. Now what we're going to do is kind of do a little mathematical trick. I'm sure you guys aren't huge fans of mathematical tricks, but this hopefully will be fairly easy to see. We want to get a relationship between this term right here and this term right here. So how are we going to do that? Well, we're actually going to do a Taylor expansion, and we're going to Taylor expand this term about this term. So I'm sure you guys have probably heard of the Taylor expansion, and it's normally something of the form of f of x with some shift in f of x plus a is approximately equal to f of a, f of x minus a, I should say. F of x minus a is approximately equal to f of a plus f dash of a, all multiplied by x minus a. That's going to be the first order term, plus the second order term, which is the double derivative. And what we're doing is we're evaluating the double derivative, and these derivatives are being evaluated at the position of x being equal to a. Important to bear that in mind. This is going to be x minus a squared, and from then on you're going to have the factorial coefficients that basically are needed to make it correct. So that is the kind of very general definition of a Taylor expansion. So how are we going to apply it to this? Well, we can see that this term is simply the same as this term, but with the shift of dy. So our kind of x right here is going to be corresponding to the dy right here. So I'll write this out. So we're going to find that ax, so this is the x component of a, evaluated at x naught and y naught plus dy, is going to be approximately equal to ax evaluated at the lower position at this point right here, plus the first order derivative dax by dy, multiplied by the shift, which is of course dy. So we've just substituted in the Taylor expansion. So from that we can see that the integral 1 and 3, so this is going to be both integral 1 plus integral 3, the original term is going to cancel. So this kind of term right here is common to both integrals, and therefore you're going to get minus dax by dy. This time it's going to be dx dy. So what I've done right there is I've added together both integral 1 and integral 3, but integral 3 I have just Taylor expanded right there. So, and I've substituted in the Taylor expansion into the integral. So instead of that we've got we've got this right here, and you guys can probably see that this term, the first term with this, will cancel with this right here, and that's just going to leave this term right here. So that is for integrals 1 and 3. Now, if we do exactly the same thing, but this time do it for paths 2 and 4, then we're going to get a pretty similar result. The only difference being is that there will actually be a, instead of a minus sign here, you're going to get a plus sign. And instead of it being the x component of A, of course, these like paths 2 and 4 are parallel with the y-axis, so therefore they're going to be just the y component of A. So you're going to get the partial derivative of the y component of A with respect to x. That's the other difference as well. It's going to be the difference. It's going to be x rather than y, multiplied by dx dy again. So this is going to be the case if you do paths 2 and 4. So if we add everything together, then what are we going to get? Well, we're going to get that the closed loop integral of a dot dl is equal to, well, it's just going to be pretty much this. These two terms are common to both, so we can put these terms at the end, and then we can put in brackets that we're going to get day by dx minus dax by dy right there. Now, what is this term right here? Well, this term right here, if we actually think about the expansion of curl, then this is actually one of the terms in the curl of a vector. So obviously when we take curl of a vector field, we get another vector, and this right here, this is actually one of the terms that we get when we take the curl. So this in fact is actually the curl of A, but it's only the z component of the curl of A. So this is in fact in itself just a scalar quantity. It's the z component of the curl of A right there. So I hope you guys remember, you can see that is in fact one and the same thing. It's just, you know, this is one of the terms when we take the curl of A, all multiplied by dx by dy. So if we generalize this to a really small loop right here, so if we imagine a really small loop, we're going to actually find that independent of the geometry, the exact same principle is going to apply. So here is our small loop, and here is the normal vector pointing out of the loop right there. So here is our normal vector. Then we find that the curl of A in the normal direction to the loop, in this case we kind of did it with z hat, but of course this will work in any dimensions. It's not specific to this dimension, it's just we happen to be integrating over the xy plane, which is why we got the z component of curl, because z is of course normal to the xy plane, is going to be the limit in which the surface area tends to 0 of the closed loop integral a dot dl, all divided by ds right here. So as you can see, the curl of A in the direction normal to the plane in which we're integrating it over is actually the really small limit. As this surface gets tinier and tinier and tinier, then you can see what's going to happen. And so all we now have to do is we then just multiply both sides by ds pretty much. So let's just go ahead and do that. So we're going to get the curl of A. This time we need to dot product with it with ds, because of course when we bring the ds up right here, it's going to be ds n hat. But more generally, we don't bother writing the n hat. We just write ds with a little vector sum pointing over. So the direction in which ds is pointing is always normal to, it's always in this direction right here. It's always normal to where the surface is. So that is curl of A dot ds is equal to the integral of the closed loop integral rather of a dot dl, and that's going to be the limit as ds tends to 0. But of course, to get rid of this limit term right here, all we have to do is integrate the left hand side, and then we don't have to take the limit anymore, and so we end up with both integrals. So this right here, you'll be pleased to know, is Stokes' theorem, and it's basically saying that the closed loop line integral that encloses a surface right here, so here's our surface, the closed loop line integral, if you do go all the way around right there, is exactly the same as if you were to do a surface integral of the curl of the vector field all across this surface right here. So they are one and the same thing, and this is Stokes' theorem. Now, the beauty of Stokes' theorem is that, say we have some kind of path right here, it doesn't have to be the surface that has the minimum amount of surface area. So it doesn't have to just be this kind of, surface that's trapped in here. It in fact could be any surface, as long as the outer loop, like the outer curve, encloses the surface. So I'll just draw like an example of that. So if you imagine sort of like, I don't know, kind of like a net kind of thing, you could do the integral over this surface right here. It doesn't necessarily have to be the smallest possible surface. It in fact can be any surface right here. So that's a particularly useful thing. Because say you have, like a surface right here, you could actually do a spherical integral over this surface right here. So, say you're having a bit of trouble integrating this line integral right here. Well, Stokes' theorem comes along, and what you can do is convert it to a surface integral, which you may find easier to deal with. It really just depends on the particular problem. But yeah, basically that's how you can get between a line integral to a surface integral with the use of Stokes' theorem. Stokes' theorem is used in the other two of Maxwell's equations. I mentioned that the divergence theorem was useful for the first two. Stokes' theorem is actually very useful for the other two, and of course it has many other applications in electromagnetism, and it's very, very useful for solving electromagnetism problems. So yeah, and just a final point to note is that if we have if we say we're doing a closed loop integral of some kind of arbitrary force, and we're going to do this loop integral all around a line right here. So let's say here's our path that we're choosing, and here's our kind of vector field right there. So we're gonna be putting in some work, and the way in which we do work is by applying a force all through around a closed path. So what did we say in a couple of videos ago? Well, we said that this integral would always be 0 if the force is conservative. Because I said that it doesn't matter what path you take, if you start and end at exactly the same point, over the course of the whole loop, no work whatsoever. So the work that you do if you start and end in the same position will be 0, provided that it's a conservative force. It must be a conservative force right there. So what does that mean? Well, if we apply Stokes' theorem, then you can see that this integral is one and the same as the curl of f dot ds. And that must also be equal to 0. Since this is equal to 0, by Stokes' theorem, this must be equal to 0 right there. So what does that mean? Well, since ds can't be 0, you know that the curl of f must be the only thing that's equal to 0 in this equation. So we know that curl f equals 0. Now, what did I say that when I was talking about curl? I said that anything with 0 curl means that means that it's irrotational. That means that there is no sort of shear or vorticity associated with this field. And so now you can see that irrotational vector force fields actually describe conservative forces. So there is an intrinsic link between whether a vector field is irrotational and whether it is conservative. And there is an easy way to show by Stokes' theorem the link between the two. So I just thought I'd mention that because it's quite an important physics concept. But yeah. So you'll be pleased to know that that is pretty much all the maths that we're going to be needing for this course right here. If there is any kind of additional bits of maths, I will just introduce them as I go. But there shouldn't be anything too much more advanced than this sort of stuff right here. So yeah, as long as you guys are comfortable with this level of maths, then next video we'll be making a start on electrostatics, which is the first topic that we'll be covering in this series of videos on electromagnetism.